Okay, so welcome back everyone to another one of these tutorial videos. So in this tutorial video, we'll be continuing our discussion of learning automata. So I sort of finished um, with describing the general sort of problem that we'll be interested in these videos that is developing a learning algorithm which, given an observation table, given a set of strings in the language, is able to deduce a minimal DFA that accepts the strings in that language and only all the strings in that language. So what I've described so far has been a bit hand wavy. So now I'm going to give you a much more sort of specific setting in which we're going to be dealing with. So this setting is actually referred to as active learning in the machine learning circles. So we will be designing a active learning algorithm. Okay. So why do we call this an active learning algorithm? Okay. The reason why is because given some unknown, so I'm using unknown as a shorthand for a language for which we don't know the predicate function, or it's too complicated to describe, and so we only have membership functions, right? So I'm sort of condensing that down to just saying, given some unknown regular language L, right? The setting in which we're going to deal with is we assume that we are interfacing with um, a teacher, right? With a teacher T, which can give us feedback on the output of A. Okay, so what exactly do I mean by this? Assume that I have a set of observations O. This is given to the learning algorithm A, and then this learning algorithm outputs a candidate DFA M prime. So M prime is a candidate DFA, right? Then what the teacher can do, right? What the teacher can do is it can do two things, right? It can, first of all, tell us, right? It can tell us whether M prime is correct, whether M prime is actually the correct minimal DFA for the unknown language. So the teacher can say, yes, L of M prime is equal to L unknown, and M prime is minimal. Or no, right? M prime is not correct. Prime is not correct. And what it also does is, in addition to telling us that M prime is not correct, it gives us a counterexample for Y. So plus, it also gives us a counter example. So what do I mean by a counterexample? I mean a string that's either in the language L, but not in L of M prime, right? Or in the language M prime, but not in the language L, right? So this would be a false negative. Um, yeah, a false negative because it's in L, but it's not in L of M prime. So that just means that W is getting rejected by M prime, where it should actually be accepted by M prime. Whereas here, this is a counterexample of a false positive. So where M prime is accepting W, but actually it shouldn't be accepting W because it's not in L. Okay. So we have this teacher where when given some observations, the algorithm A returns a candidate DFA, then the teacher tells us yes or no whether it's correct, right? So that's sort of necessary because at some point we need to know whether we should terminate the algorithm, the learning algorithm, or whether we should keep going. So this is the first thing that the teacher T can tell us. The other thing that it can tell us is essentially how to build up the set of observation tables. So what are the memberships, right? So what are the string memberships? So the second thing it tells us is, if now I'm thinking of expanding my observation table because I need to add more data, so to refine my candidate DFA, then I think, well, I need to know whether this string W is in L or not, and so I give it to the teacher T, and then the teacher T tells me yes if W is in L, and no if W is not in L. Okay, so this is what we mean by the problem of learning automata in the active learning setup. Okay, so we're sort of given an unknown language L for which we want to develop a DFA. And the only thing we can do is interact with this teacher, which um, when we sort of generate a candidate DFA, it tells us if it's right or not. And if it's not right, it tells us why. And then it also allows us to sort of expand the set of observations by sort of querying it with individual strings, right? So notice the T here is also why I was using T of W equals 1 here, because we're actually going to see these T of W's are going to be part of the observation table. So now, at this point, I think many of you might be very puzzled, right? You might be very puzzled because I'm saying we want to generate a candidate DFA, right? Or the correct minimal DFA. And I'm saying T knows that correct answer and it can tell you yes or no whether a string is in the language. Well, then it just sounds like we do have the minimal DFA, it just sounds like it's T, right? So the answer or like the question that sort of comes up is why not T? Right, so why can't you just use T? Well, I think this is a fairly natural question to ask, and one that even I had at the beginning when I was studying learning automata. But the reason why is imagine this kind of scenario, right? So, for example, imagine you're a machine learning engineer. So uh, you're a machine learning engineer. Congratulations. You work at, let's say, Google, right? You're a machine learning engineer, and you want to design uh, an algorithm. So this is going to be our stand-in for a DFA, which let's actually call this, be a bit more specific. You want to design a classifier. So a DFA is nothing but a classifier on strings, right? So a classifier which um, checks whether uh, a research article, let's call it RA, is interesting, right? Slash proposes a novel research idea, right? So this is something that people in NLP, my area of research, are quite interested in. We always sort of we ask these sort of meta questions on how do I know if a paper is interesting? How do I know if a paper provides the community with novel insights, right? And suppose you're a machine learning engineer and you want to say, well, let me just automate this problem, right? Let me just automate this problem and automate the solution by saying, um, let's avoid researchers having to read papers and let's just have some classifier, right, or stand in for a DFA to give us the answer to this question. Okay. Well, then, what might a machine learning engineer do? Now, let's, for the sake of argument, imagine that the machine learning engineer has a very limited set of tools. So we're really talking about machine learning in the sort of era of the 80s and the 90s, where machine learning didn't really exist. It was more like expert systems. So imagine you're designing an expert system. Okay. So an expert system in sort of classical AI was this fancy word that people used to just mean a program with a collection of if then else statements. Okay. So, an expert system for our problem would be a system that takes in a research article, right? So like an 8-10 page research article about, computer science, about theoretical computer science, whatever. And the expert system, goes word by word through the research article and goes through its if then else clauses to see whether the paper meets this criteria of being interesting, right? So how might one design those kinds of rules? You might say, well, does the method section mention any new sort of buzzwords, right? Does it mention something that hasn't been seen in previous literature, right? Um, Something along those lines, right? Some of these rules would be really like hard coded by the machine learning engineer. Well, this is a difficult task sort of inherently, right? Because the machine learning engineer has to sort of sit there and kind of be like, what rules are useful and discriminative for determining whether a paper is interesting or not. And so in this setting, what a machine learning engineer might actually do is they might say, I'm not going to think about this myself. I'm going to go to an expert, right? So in this case, the expert is sort of the stand-in for the teacher, right? So now imagine you don't want to do this by yourself. So you go to an expert researcher, right? You go to an expert researcher, and this expert researcher is really good at sort of reading a research paper and telling you, yes, it proposes something interesting and cool. No, it doesn't. We've already seen what this method does. It's not at all sort of a contribution to the community, right? So this expert researcher is one really good at classifying interesting papers. Classifying interesting papers. And two, has some intuition, right? So has some intuition on what makes a paper interesting, right? So then what you can do as a machine learning engineer, you can be like, well, here are a bunch of sample papers that I have, and you give them to the engineer, to the researcher. The engineer gives these to the researcher, and they go, yes, that's interesting. No, that's not interesting. Yes, that's interesting. No, that's not interesting. So the first thing you do from that is, you develop rules based on that collection of data, right? That collection of observations. And then once you sort of create these rules that you think fit these observations well enough, then you say, okay, I think I'm satisfied with my sort of expert system matching the observation data. Now let me go to the researcher, right? Let me go to the researcher and ask them if they think these rules are reasonable, right? And because the researcher has a very good intuition as to what makes a paper good or not, but is not really is not great at sort of verbalizing that, then what they do is they sort of can just inspect your rules and say, oh yeah, that kind of makes sense, right? So that would be in sort of this category of the teacher being the researcher saying, yeah, I think your rules are reasonable and this would be a good production system, right? Or they can say, whoa, 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 there's something flaringly wrong about your system, right? Because here, let me give you another example of a paper that is just a bunch of literature review. And that's not interesting at all. That's just like a survey paper, but it doesn't propose a new idea. So then, it would say, well, your system doesn't account for this. So I'm going to tell you, no, your candidate system is wrong. And I'm going to give you a counterexample, in this case, another paper. Then, what you would do is you would say, okay, let me integrate that new piece of information into my system and let me sort of redevelop another system that matches this new set of data. And let me go back to the teacher or the researcher and check whether that's correct, right? So this is the setting of active learning we're in. That's why I think, the way I've described it, I feel like it's maybe a little less toy. And so that's how that's the main motivation of why this setup was sort of brought up. And so in the next videos, we'll be looking at how exactly you can first of all um, develop an observation table from membership questions, how you can then take membership questions and answers to the teacher, take those observations and convert them to a DFA. So this is sort of the analogy to the expert system. And then take this DFA, present it to the teacher, and if the teacher gives you a counterexample, meaning that your DFA is wrong, how can you constructively use that feedback to um, make your DFA more correct, right? So that's what we'll be studying in the next videos, and so hopefully you're still with me and you're still interested enough to watch the next.